Yeah, thank you very much, Yunsi. So, as you already mentioned, I'm here today to present the work where we had a look at how the publication of expected star distances actually has the potential to improve efficiency. And I worked on this paper together with Raphael Monstein that we just saw, also Timothée Kraut, both from ZHW, as well as also with Jan Allendorf from Swiss International Airlines. So before I start with the actual work that we did, I want to provide you with a brief introduction to try and highlight the actual problem at hand. And here I maybe first need to mention what a star actually is, since I will mention this word many times during the presentation, just in case somebody doesn't know what it is. So STAR stands for Standard Terminal Arrival Route, and it's essentially just a predefined air traffic service route, which is there to lead IFR traffic from the en route segment to a specific fix, from which they then usually commence an approach down to an airport. And during pre-flight fuel planning, or more specifically to determine the amount of trip fuel that is required for a flight, one aspect that is considered is the distance of the nominal star procedure, which is expected at the destination airport. But of course, in reality, it can happen that air traffic control will provide shortcuts, which then means that a certain portion of the star is bypassed, resulting in shorter distances that are flown. We then, however, learned that in some cases, for some stars, the provision of such shortcuts is systematic, therefore then also leading to systematic discrepancies between the distances that are used for fuel planning and the ones that are actually flown. And one good example to illustrate that is the Belus 3N star at Geneva Airport, for which, as per official published procedure, as shown here in the left animation, the aircraft is supposed to first fly a upwind leg along the approach path at higher altitude, then turn right for a 20 nautical mile downwind, before then turning base for the actual approach down to runway 04. But what happens in reality is that essentially all aircraft are provided a more or less straight-in approach to the Indis waypoint, from which they then directly initiate the approach down to runway 04. And in terms of distance, the difference between the two, so the nominal procedure and the one that's actually flown, is about 50 nautical miles, meaning that aircraft that plan their fuel based on the nominal procedure end up carrying about 50 nautical miles worth of trip fuel, which in the end is never used. And this is a problem that is not unique or isolated to this one-star procedure at the Geneva airport, but rather there's also other stars at other airports which are in a similar situation, which is why some ANSPs have actually started to publish expected star distances in the respective AIPs, which can be used by operators for flight and fuel planning purposes. So here we see two examples of that. On the left, we see an extract of the AIP for Munich Airport, where they provide the expected distances for 8 different star procedures. And they specifically mention that these can be used for flight and fuel planning, and that any distance which is flown in reality that's longer than these expected distances can be regarded a delay situation. On the right, we see a different example of the AIP for Rome Fiumicino Airport. Here they chose a slightly different approach. They also provide expected shorter distances. These are, however, only valid during out-of-rush periods, whereas during defined rush hour periods, operators are supposed to do their fuel planning based on the full star procedure distance. So after we had heard about this problem and this interesting approach of publishing these expected distances, we thought that it would be a problem that is worthwhile exploring using historical trajectory data, which is why we decided to do just that, using the specific examples of Geneva, Munich, and Rome Fiumicino Airport. And we thereby had two main objectives in mind. So first, we wanted to see how the actual flown distances compare to the full star procedure distance, and were available also the expected distances. And in a second step, we thought it might also be interesting to try to estimate how much fuel could be saved when expected distances are available for a specific star procedure. But before doing any of that, of course, as always, we had to prepare the data that was required to do just that. And here we first selected a subset of 4 star procedures for each of the 3 chosen airports, and that was mainly done just to limit the scope of the work a little bit. And we hereby prioritized the star procedures which had a high shortcut potential. And in the cases of Munich and Rome, we also only considered stars for which, of course, expected distances were available in the AIPs. We then collected all available ADS-B trajectory data corresponding to flights that followed one of these selected stars during the year 2023. And of course, here we got our data from the Open Sky Network historical database. And based on these trajectories, we then generated 1 data frame per airport, which summarizes key information about each of the flights, such as which landing runway was used, which star procedure was being followed, and most importantly, what distance was flown by the aircraft from the initial waypoint of the star to crossing of the threshold of the landing runway. And based on these data frames, it was then pretty easy to generate plots which show us the distribution of observed actual flown star distances for all the different stars that we selected. And here we see the corresponding plots for the 4 stars at Geneva Airport. Hereby the blue violin plot with also overlaid box plot shows us the distribution of the observed distances that were flown, and the red horizontal line additionally indicates the distance of the full star procedure as published. So here we can see in Geneva for these 4 stars, the results are a bit twofold. So on one hand, on the right side, we have the stars Kines 2N and Lusar 2N. For these 2, the majority of observed distances are slightly shorter than the full star procedure distance, however, only a rather slight discrepancy. However, the other 2 on the left side, the Belus 3N and Akito 3R stars, here we can see we have a much more notable discrepancy between the full procedure distance and the majority of observed ones. In fact, for these 2, the discrepancy between the full distance and the median of observed ones is more than 40 nautical miles in both cases. Then here we see the same plots for the 4 stars that we selected at Munich Airport. And as we can see here, we have a bit more of a uniform picture. So we have similar characteristics for all 4 of them, with, again, notable discrepancies for all 4 procedures. But here, of course, we have to keep in mind that we saw in the introduction that we have these expected distances available in the AIP. And if we overlay this information of the expected distances for each star procedure as a green line, we can see that they are quite a bit shorter than the full star procedure distance and closer to the majority of observed ones. But still at a distance which is slightly longer than the majority of observed ones. And that is confirmed if we check at what percentile of the observed distribution the expected distances correspond to, since we can see they correspond to the 95th, 94th, 91st, and 95th percentile. So meaning that throughout 2023, still more than 90% of all flights that were observed flew distances that were shorter than the published expected ones. And then 3rd and final airport, we have Rome Fiumicino. Here again, somewhat similar overall picture with some discrepancies between the full procedure distance and the majority of observed ones. And here, of course, again, we have the published expected distances available, which are somewhat closer to the majority of the distances that we observed. But here we have to keep in mind that the expected distances are only valid during out-of-rush periods, which is why it makes a lot more sense to actually look at the data separated by this criterion. So we see here the distributions, but separated by landings that landed during rush hour periods or out-of-rush hour periods. And when only considering the out-of-rush hour periods during which the expected distances are valid, we see again that the expected distances correspond to the 94th, 93rd, 85th, and 90th percentile. So again, a somewhat similar overall picture. So this first part has already clearly shown that there seem indeed to be some discrepancies between the full start procedure distance and the ones that are actually flown. But we then thought that it might also be interesting to see how much fuel can actually be saved when providing these published expected distances for a start procedure. So to try and do that, we worked with a fictional flight of an Airbus A220 flying the route from Porto to Geneva on the 10th of October 2024. And that uses in Geneva the Belus 3N star. And we chose this specific star since during the first part of the analysis, it was the one that has shown to have the biggest discrepancy between the median observed flown distance and the full distance. And also since it is a star for which expected distances are not yet available, so that maybe with this analysis we can show that it might be worthwhile exploring published distances for this one as well. And the route from Porto to Geneva was chosen since it has a flight duration of about 2 hours, which perfectly aligns with the flight duration of an average short-haul flight operated by Swiss International Airlines into Geneva. Based on this fictional flight, we then created realistic operational flight plans for 3 different scenarios using the CAE Flight Plan Manager software. And thereby the majority of variables or parameters across the 3 scenarios actually remained the same. So we used the same typical aircraft weight and also overall route. We used the same weather conditions that actually reflect the weather conditions of that 10th of October 2024. And we also used the same alternate fuel to Lyon Airport, 5% of contingency fuel, and 20 minutes of discretionary fuel, which is also realistic for this city pair or this route. What, however, differs between the 3 scenarios is how much fuel is carried by the aircraft to fly the start procedure and how the start procedure is actually flown. So for a first scenario, we have the aircraft carry fuel to fly the full start procedure and also actually flying the full start procedure, which results in a requirement of 3,667 kilograms of trip fuel that is required to perform the entire flight. In the second scenario, we then created essentially the situation as we have it today, where the aircraft carries fuel as well to fly the full start procedure, but in fact flies a straight-in approach using the waypoints Belus, CBY, and Indis. And for this scenario, a total of 3,423 kilograms of fuel are required for the entire trip. And in the third scenario, we then created a situation where we assume that expected distances are available that more accurately reflect the actual distances flown. So the only difference to scenario 2 is that we don't carry the fuel for the full start procedure, but only the fuel that is actually required to fly the straight-in approach. And here the amount of fuel that's required for the trip is 3,413 kilograms. So we can see between scenario 2 and 3, we have a difference of 10 kilograms of fuel that are required for the flight, which is only due to the fact that in scenario 2, we carry the additional fuel to fly the full start procedure, which is in the end not done. So now you might say that 10 kilograms of fuel that could be saved, that might seem like not a lot at all. However, when summed up across multiple flights over a longer period of time, that quickly sums up to significant savings. So if we only consider one comparable flight that uses the Belus 3N approach over a year, that already sums up to 3,650 kilograms of fuel. And if we assume that 10 flights a day would use this approach, similar flights to the one that we consider here, we already end up with over 36 tons of fuel that are saved every year. And just as a reference, in the data set that we created for the first part of the analysis for Geneva, we had almost 4,000 flights using the Belus 3N star in the year of 2023. And that amounts to an average of 11 flights that use this star every day. And we also have to consider that here in this example, we use the short-haul flight of an Airbus A220, which is a rather efficient and small aircraft. And for larger aircraft and particularly also longer routes, the potential savings are even much greater. And with that, I already come to the conclusion of this presentation. So what are the most important takeaways of the work that we did? So we have shown that for stars, indeed, it can be the case that significant discrepancies between the procedure as it is published, the distance of this procedure and the actual distances that are flown exist sometimes. And we have also shown that for cases where we have published expected distances available in addition, that these help to correct these discrepancies, thereby better aligning flight planning and also fuel planning with reality. With this specific example for the Belus 3N star, we could show that for an average short-haul flight of about 2 hours, up to 10 kilograms of fuel could be saved when publishing expected distances. Overall, I think we have shown that it is a simple and effective way to address these specific discrepancies for specific stars that suffer from this problem, and that a broader adoption of this approach could lead to significant reductions in unnecessary fuel burn. And while here we only talk about the positive effect in terms of less fuel that is burned, having expected distances available also has other positive side effects. One of them being that it might help flight crews to better perform their descent planning if they have a better idea about the track miles that are to be expected. That's particularly the case when flying into airports that are rather unfamiliar. And with that, I'm at the end of this presentation and I'm open for potential questions.
Thank you very much, Ian. Any question from audience?
Thank you very much. Very interesting presentation. In any case, this presentation you made today and others that are floating around in this seminar and in others are trying to obtain benefits for very small things that are planning margins that the people left. In your own presentation, you say that there are 20 minutes flying discretionary fuel charging. Mm-hmm. I suppose if you publish this expected distance and then they should fly the full flight, they will be taken from the other, from the 20 minutes maximum. Because if it is not the case, you will start having the fuel from the alternative airport. That means that if after the full maneuver you don't have, you are not allowed to land, you will be sent to alternative airport with not enough fuel except the 20 minutes. So the question is, do you consider that those margins, is my belief, should be reduced in a way that all of them don't add one on top of the other? Is what is happening in our business because of safety normally? Mm-hmm. Or you believe that should be solved one by one, independently, and cut all of them at the same time?
Well, I think here in this case, since it's a phenomenon that's particularly caused just by these star procedures, I think here it would make sense if you really have these systematic discrepancies to address it this way by publishing expected distances in the AIP that allows you to adjust the trip fuel and not play around with discretionary fuel and stuff like that. And yeah, maybe I didn't really understand the question properly.
Just an extra explanation. Sorry not to be so clear at the beginning.
No,
this is one of those marginal things that we could improve. If we treat every one of the marginal things, as you suggested, we treat this one, at the end we will remove the margins. That's the problem. And you need margins somewhere. So we should treat the things in an aggregate way, not one by one separately, because if that's the case, every margin will disappear. That could be good if we always run the things on the proper way, but when things happen, you will have problems on safety.
Yeah, but I think if it's really that systematic, as we have seen, for example, for the Belus 3N, where we really have essentially all flights that fly much shorter routes, it's really maybe 1 or 2 flights a year that fly the full procedure distance. And I assume it's in cases where you maybe have really bad weather or stuff like that. And in these cases, then usually, I guess, the pilots add an extra margin by taking some discretionary fuel in addition. So I guess you can compensate for that in this way. But yeah, you always have to ensure that it's still done in a safe manner, of course, yeah.
So, well, again, it was a very good presentation and work. I have 3 quick questions. So the first one is, do you know if right now airlines are working in the second scenario? I mean, do they plan with the full star, or are they actually using what they fly every day?
I mean, I can't talk about all airlines. I only know about one, and they do it that way. So they carry the fuel for the full star procedure, but then always fly the straight in one, because otherwise you wouldn't comply anymore with the EASA regulations on fuel stuff.
So the second question, well, it's not a question, it's a suggestion. So usually the average fuel for a flight in Europe is around 6,000 kilos or something like that. What is inefficiencies that you can apportionate to inefficiencies in ATM, around 10% as a maximum. So that 10 kilos of savings you need to put in terms of the, 500, 600 kilos that may be accounted for these inefficiencies, and maybe it seems low, but, we don't have so much margin. Mm-hmm. And the third question, and now is the question, because I noticed that you changed a little bit the title of the paper and the title of the presentation.
Yeah, I don't know where this title came from. That is in the official program. I never defined that title. I don't know where that appeared from.
But do you think it would be feasible to predict when these full stars are more likely? In order to...
I mean, that would definitely be an interesting approach, because I think oftentimes when longer distances are flown, it's, for example, due to effects such as weather, and therefore it would be interesting to do that in a dynamic manner, that you adjust the expected distances based on weather phenomenon or depending on the time of the day and such things. So that would definitely be an interesting approach, yeah.
So a little bit on the economics, maybe it's just one case a year that you need that extra fuel. But if you have an accident and that factor contributed, it can cost 500 million euros.
Yeah.
So, sure. I mean, the cost of mitigation, you need to consider that. Okay. Thank you.
Thank you, Christian. Here and then.
Hello, thank you. I have a question. So here you focus on the benefits of not carrying extra fuel. Did you analyze also the potential benefits on vertical descent profile, as when there is a huge discrepancy between the planned procedure and the flown inside aircraft? The flight management system is fully shitted because the flown distance is not the one it predicted, so it cannot predict the good descent profile. So generally, the descent is initiated by the controller who know the airport, and they know that the aircraft do not have to be in over energy because they will not run all the circle. But it's again not efficient because the controller do not know the aircraft performances and so on. So did you make any analysis on the potential benefits on not on extra carrying fuel, but on the possibility to optimize the vertical descent profile due to the knowledge of the real descent length?
No, I did not do any analysis on that, but I'm pretty sure that it will also have an impact on that for sure.
Thank you very much. Just to respond a bit to what you say, I think it's when you reduce the amount of fuel you carry, your chance of having to divert increases. And probably you'd have to just find the sweet spot where you can reduce the amount of fuel carried without really increasing substantially the probability of having to divert. But I think since other airports are already doing that, and making these numbers available and they're operationally used, I would assume that because airlines obviously have a financial interest to not divert too much, I think it's probably justified and probably not decreasing the safety margins by too much. just a comment to you, I would also always add another number, and that's the fuel times 3.16 to talk about the safe CO2 emissions. It's also that.
That's also nice that emissions
It's also
are
nice.
safe,
Thank you.
Any other questions? Like this one and yeah.
Hi, thanks for the nice presentation. I think it's a bit of a follow-up question from one of the other questions we had. Did you investigate a bit on how these expected distance are computed, or how do they come up with those? Do you know?
I don't know, but I heavily suspect that it is also determined by looking at a certain amount of time, the actual flown distances, and then just taking a specific percentile, because I find it a bit suspicious that it's all somewhere around the 90th percentile. So assume it's done that way, but I cannot tell you whether it's really done that way. It's just an assumption on my side.
So you're saying it's like, in your opinion, it's more like an empirical thing. It's not really depending on some.
That's what I think, but
yeah,
I don't know. Yeah.
Okay. Yeah, it could be interesting to understand that. Yeah. Thanks.
José Miguel.
Thank you very much. It was very interesting when you answered one of the previous questions, and I believe it was Christian the one put in, telling that the airlines charge, even knowing, because they should know, it's his business, that they will be sent 100%, 95% of the times for the shorter route, they charge extra fuel. Do you know why?
No.
I guess, because I don't know. It's because of responsibility. Simply because of responsibility. They believe they have a chance, small, but a chance to flow the longest one. And exactly because of responsibility, they do that. If you publish shorter route, you are taking the responsibility, because if then the flown route is longer, the problem is yours. You have said something different. That's the point where academics differ from reality. Thank you.
Thank you. That's a very good comment. Maybe it would also be interesting just to look at your data, right? So if you take the shorter route, how many of them actually had to fly in a longer route? And then we might be able to quantify those percentage of the flights where you might run into problems.